Hi everybody. It is Sunday, February 2nd, 2025. This is the second of your baby lectures. So before we start, make sure you're sitting comfortably. Be with a friend or a classmate if you can. Have a paper and pencil ready, and a calculator as well. You would be doing some calculations. So what are you going to see in this video? In the first part, we're going to look at chi-square tests. So I'm going to give you an example of a chi-squared independence test. I'll give you some data and you will do some calculations. And after that, I'm going to go through 6 scenarios where you have to guess which of those chi-squared tests is most appropriate. The new part for this video is really not that new at all. We're going to review linear regression. So this will be a review of some of the concepts you learned in 2208 in preparation for some new concepts about regression that you're going to learn in this course. So let's remember what we learned in the last lecture, the chi-squared independence test. So this is where you're given counts for various combinations of 2 categorical variables in a contingency table. And you're asked whether the 2 categorical variables are associated or dependent. The counts are drawn from one population. The null hypothesis is that the 2 categorical variables are independent. A key thing to remember here is in this scenario, we have 2 categorical variables and a sample drawn from a single population. So here's an example. Here we're looking at a table. This is a contingency table. We have on one side injury site. That's one of our categorical variables. It has 3 categories: body, head, and limb. And then we have lethality, the lethality of the injury, whether it was fatal or not fatal. So here, this data was collected from 146 emergency room patients, randomly selected from the population of ER patients involved in traffic accidents. So let's test to see if there is evidence that some types of injuries are more lethal than other kinds. In other words, we're going to test to see if lethality and location are dependent or independent. So this is a chi-squared independence test. And how do you know? We have 2 categorical variables. And the independence test is the only test where there are 2 categorical variables. And furthermore, we're drawing a sample from a single population. The null hypothesis is that lethality and location are independent of each other. The alternative is that they are not independent, or in other words, they are dependent. So at some point, we're going to look up a critical value. But before we do, we have to determine the degrees of freedom for our chi-squared test. So do you remember how to calculate degrees of freedom when you have a contingency table? First of all, you have to realize that the part of the table you need to look at is where the data is. So we ignore the margins when we are determining the degrees of freedom. And what we want is the number of rows and the number of columns in that part of the table. So here we have 3 rows and 2 columns. We plug that into the equation for degrees of freedom, we get 2 degrees of freedom. So you can see the number of rows really is the number of categories in the first categorical variable. The number of columns is the number of categories in the second categorical variable. So here we're working with 2 degrees of freedom. So I'd like you to look at this table and just pick out what the critical value would be if we were to conduct the test at the 1% level of significance. So you should be looking at the row for 2 degrees of freedom and the column for 1% level of significance. The critical value is 9.210. So what can we do with that? We can make a sketch of our decision rule. And I'd like you to pause the video right now and just try to make a sketch of the decision rule for our test. Just see how far you can get, see what you remember. Pause the video now. So the sketch should look something like this. We have our critical value, 9.210. That puts 1% into the upper tail. and our rejection region marked in red. What's our decision rule? We will reject the null hypothesis at the 1% level of significance if our test statistic is greater than this critical value, 9.210. So what's next? We need to calculate our test statistic, and the first step of that is to figure out what we would expect to see for each contingency if the null hypothesis was true. So on the left-hand side, we have our observations. On the right-hand side is a table where we can write in the expected values. Remember how to calculate expected values. Here, I want you to pause the video, take 5 or so minutes, as much time as you need, in fact, and to calculate the expectations for all 6 of these contingencies. Please pause the video now. So let's see, make a comparison of what you got and what I got. These are the numbers I have. Now, what do we do with these numbers? We have now observations, and we have what we would expect to see on average if the null is true. What do we want to measure about these things? We want to measure how far apart they are. We want to measure the statistical distance between what we observed and what we would expect to observe on average, what we expect to see if the null hypothesis is true. Remember, the bigger that statistical distance, the less likely it is that the null is true. So how do we calculate that distance? Well, first, it's convenient to put these values into a table. I forgot there was something important I was going to mention here. Yes, okay, let's put a hold on calculating the chi-squared statistic. I put a little box around this number 1 because I wanted to ask. Here we have one of those contingencies where there's only one patient, so the observed value is 1. Is that a problem? Does that mean we cannot proceed, or is it not a problem? So some of you may know what I'm talking about. What I'm getting at is just to remind you that one of the conditions for us to conduct this chi-squared test is that the expected counts must be at least 5. But this 1, that is an observation. That's an observed count. That doesn't matter. The fact that that's a 1 doesn't matter. All that matters is our expected counts, which are on the right-hand side, are all 5 or more. So just going through the conditions for the chi-squared test, for this chi-squared test of independence, we have 2 categorical variables. We have 1 population. It's a random sample, and what I'm getting at here is the expected counts need to be 5 or more. So the fact that an observed count is less than 5 doesn't matter. It's the expected counts that matter. So I just wanted to emphasize that. Let's get back to calculating the chi-squared statistic. So you can see here we have in the first column the observed counts. In the second column we have what we would expect to see if the null hypothesis was true. And in the blank column we're going to fill in our values for the chi-squared components. So remember how to calculate those. You take your observed value, you subtract the expected value, that's a deviance. You square that and then divide again by the expectation. So here's the point again. Pause the video, take 5 or 10 minutes, calculate the contribution to the chi-squared statistic for all 6 of these observations. Please pause the video now. Okay, so you should have the values that you're seeing here. So these are the contributions to the chi-squared statistic made by each of the observations. What do we need to do with these contributions? We need to add them up. So you add them up and you get finally your chi-squared statistic. So looking at that chi-squared statistic, what do you think? Do you think that's big or small? You should be thinking that's pretty big. And how do you know that? Well, let's go back to our decision rule. We already said ahead of time that to conduct a 1% test, we're going to reject as long as our test statistic is bigger than the critical value of 9.210. So clearly here, we're going to reject the null hypothesis. So the test statistic is much, much greater than the critical value. So we reject the null hypothesis and conclude that for the population considered in this study, the lethality and location of an injury are dependent at the 1% level of significance. So what's the p-value for the test statistic? Just take a minute and think about what that p-value would be. The key here is to realize, first of all, that if our test statistic was 10.597, so if it was this value, then the area in the upper tail would be 0.005. In other words, if 10.597 was our test statistic, the p-value of the test would be 0.005. But our test statistic is way off the chart, far, far to the right. And so the area in the upper tail, the corresponding p-value, is going to be much less than 0.005. In fact, it's essentially going to be 0. And so we can say the evidence against the null hypothesis is very strong. Now, one last thing I want to talk about in this scenario, just want to discuss the kinds of things that you might infer depending on how the numbers work out in this calculation. So what I'm getting at is I'm going to ask the question, what is driving the dependency, right? So we rejected the null. We can conclude it that these two categorical variables are dependent. In other words, the probability that an injury is fatal depends on the location of the injury. Now, the question is there any one contingency that is contributing the most to the chi-squared statistic? And the answer is, well, yes, there is. It's the contingency where the injury is a limb injury and it's non-fatal. So you can see from the table, the first table, you can see we observed 21 out of 146 patients who had non-fatal limb injuries. If the null hypothesis was true, if the fatality and location were independent, we would expect to see, in a sample size of 146, we would expect to see 6.52 patients in that contingency on average. So that's much, much smaller. So what is that telling you? The biggest contribution to the test statistic by far is caused by the difference between the observed and expected number of non-fatal limb injuries. And what this tells us is that the probability that a limb injury is non-fatal is much higher than would be expected if lethality and location were independent. Right, so this is the kind of interesting thing that you can infer from the chi-square test and from these calculations. Okay, so let's just talk once more about the assumptions for the homogeneity test. Two categorical variables, samples from one population, it's a random sample, and all expected counts are 5 or more. Okay, so this is the end of our unit on chi-square tests. And so we have 3 chi-square tests in total, so it might be helpful just to summarize those once more. So a goodness of fit test, you have one categorical variable drawn and a sample drawn from one population. For a homogeneity test, you have one categorical variable and a sample drawn from 2 or more populations. And for the independence test, it's 2 categorical variables and a sample drawn from one population. So you might want to take a moment, just pause the video, and just write down the part that's in the brackets for each of these 3 scenarios. And you can use that as a guide, because what I'm going to do next, I'm going to show you some scenarios. You just read this scenario, and then you have to figure out which of these 3 models applies. So pause the video now if you want to just jot these down to help you with what's coming. So here are our examples. And before I start, let me just say, there's going to be 6 examples, but some of the examples are not appropriate for a chi-square test. And so how can you tell? Well, remember, chi-square tests require categorical variables. Just keep your eye out. In at least one scenario, there's just sort of hidden in there, there's a quantitative variable, right? And so in that case, you have to say, I cannot use any of the chi-square tests because there is quantitative data. So just keep an eye out for that. Okay, so here's the first scenario. A student wants to find out whether political leaning is related to the choice of major in university. She surveys randomly selected students and performs a test. Just take a moment and think about which of the 3 tests applies in this case. So here, it's a chi-square test of independence, because There are two categorical variables. There's political leaning and choice of major. Those are separate variables, and each one is categorical. And you can see that the population is just one population. It's a survey of randomly chosen students, so it's a single population. So that's clearly independence. Let's try another one. Here is the quality of a car affected by what day it was built. A car manufacturer examines a random sample of the warranty claims filed over the past 2 years to test whether defects are equally distributed across days of the week. So what kind of test applies in this case? So here we have one categorical variable, that's days of the week, and we're drawing samples from a single population. Those would be cars that were manufactured at some factory. So one categorical variable, one population, that's a goodness of fit test. Try another one. Here, the academic research office at a large community college wants to see whether the distribution of courses chosen is different for its residential and non-residential students. It randomly selects students and performs a test. In this case, we have a single categorical variable, that's the courses chosen, and we're drawing samples from two populations, the residential students and the non-residential students. And so this would be a chi-squared homogeneity test. How are you doing so far? Let's try a few more. Here, a medical researcher wants to know if blood cholesterol level is related to heart disease. She examines a database of patients, testing whether the cholesterol level in milligrams is related to whether a person has heart disease. What kind of model applies in this case? Aha, so this is a bit of a trick question. We need some other statistical tests in this case. And why is that? Because although heart disease is categorical, whether or not someone has heart disease, it's yes or no. That's a categorical variable. The cholesterol level is quantitative, and so we cannot use a chi-square test in this case. Next one, a brokerage firm wants to see whether the type of account a customer has affects the type of trades that customer makes. It collects a random sample of trades made for its customers over the past year and performs a test. What kind of test in this case? So here it looks like we have two categorical variables. It's the type of account and the type of trade. And furthermore, we can see that the sample is drawn from a single population. And so the firm should use a chi-squared independence test. Let's do one more. Here we're pretending that the same brokerage firm wants to know if the type of account affects the size of the account in dollars. It performs a test to see if the mean size of the account is the same for all three account types. So what kind of test is it in this case? So who said that it's not any of the tests? That's the case here. We do have a categorical variable. It would be the type of account, but the size of the account in dollars is quantitative. And so we cannot use a chi-square test in this scenario. Okay, so at some point in the course, we'll be doing more examples like this. By the time you get to the exam, you're going to have in your toolkit, if you will, probably 8 or 10 different models. And it's really important that you understand when a given model applies. In other words, it's very important that you can read a scenario and figure out which of those models is appropriate for that scenario. So we'll be doing some more practice of this as we go. So it is, well, it's not Thursday, it's Sunday for me, but this lecture is for Thursday. So it's time to go through your homework for the next week. So first thing, review the slides from this week. Don't forget that it's really important to review the slides the day of the lecture or the day after. The sooner you do it, the more you're going to retain, more information you're going to retain. And that's going to facilitate your learning process. So be sure to review the slides from this week. Read Module 5. That's the module about inferences for regression. So that's the section that we are going to start when I see you again next week. There's Skill Check 8 is posted in the Moodle. That's for the chi-squared independence test. You can do that skill check and then look at the video solution. Homework 4 in my lab, that's also all about the chi-square tests. The original due date for that was Monday. I decided to change that to Wednesday the 12th to give you some extra time. So make sure you get at that soon. You already know everything you need to know to do that, so you can start on that right away. And don't forget that you have a quiz that opens this coming week. It's February 6th. That's Thursday, February 6th. That would be today if you're watching this on Thursday. And the quiz closes the following Saturday. I'll give you more details in a moment. The last thing to just tell you is that your lab, not this coming week because today is Sunday, but the week after that, that lab that's coming following next Thursday is going to be about chi-square tests. So you already know everything you need to know to handle that lab. Right, so about the quiz, again, it opens on Thursday the 6th. It'll open at noon. It closes just before midnight on Saturday. I strongly recommend you do the quiz on Thursday or Friday. If you leave it to Saturday, there's a chance something will go wrong and you miss it. You don't want to miss a quiz. I can't give rewrites for quizzes like I can for assignments. So please make sure you complete that quiz. Don't forget that you can do the quiz twice. You do it once, you see what your score is, and then the same day or the next day, you can do it again, maybe revise your notes first, try the quiz again, see if you can get a better mark. The final mark you get would be the highest of the two. The topics for the quiz include 2-sample t-test, paired t-test, and in both scenarios, confidence intervals for those. So if you want to get some practice for that, in the first baby lecture from Tuesday, I give examples of both of these scenarios where we calculate confidence intervals and we conduct hypothesis tests. So that would be a good place to look. And of course, you can also go through the skill checks for those two topics as well. That will make sure you're well prepared for this quiz. Okay, so let's go back to linear regression. This is a topic that was introduced in 2208. So I'm going to just go through and refresh your memory on some of the concepts. And certain of the concepts which I feel are more important for what is to come, I will emphasize those ones. So we start with a scenario. So here we're pretending that at a local chess club, a local chess club randomly selected 25 novice students to participate in a new online chess training program. The students were encouraged to use the training program for as many hours as they wanted. After a 1-month trial period, the playing strength was assessed for each student. So the first thing to recognize here is that we have two quantitative variables. First one is the number of hours a student chose to engage with the online training program that month. And the second is the playing strength of that student after 1 month of using the online training program. So two quantitative variables. This is the hallmark of a linear regression scenario. So let's talk a bit about the data. Here on the left, you can see our coordinate system. On the horizontal axis, we're going to put the number of hours a student spent using the training program. On the vertical axis, their playing strength at the end of that 1-month period. And what do we call X and Y here? We call X the predictor or the independent variable. And Y is the response or dependent variable. And the whole idea is that we want to build a linear model so that we can use X, in this case being hours of training, to predict Y, that being the chess playing strength at the end of the training period. So the fitted linear equation or regression line models the linear trend in the data. And so that linear trend is represented by an equation like the one you can see here. So let's look at the parts of this equation just to remind you. So first of all, we have this thing we call y hat. This is the fitted or predicted value given the value of a predictor x. Next, the regression line is characterized by two numbers. The first is the y-intercept. We give that the symbol B0. The y-intercept is the place where that line of best fit crosses the y-axis when x is equal to 0. So B0 is the y-intercept. It gives the value of y hat when x is equal to 0. The second number is called the slope, and the slope tells you that if the x value were to increase by 1 unit, it tells you how much the y value will change by. Right, so B1 is the slope of the line. It gives the amount by which y hat is predicted to change when x is increased by 1 unit. Okay, so let's make things a little bit more concrete. So what you're seeing at the top of the screen is Minitab output. We use Minitab to calculate the slope and intercept, and so you're never going to need to calculate these things yourself. They're always going to be either given directly or they're going to be displayed in a table, and you have to understand how to read the table to get that information. So here we have a column called COEF. That COEF represents coefficients. So this column shows our model coefficients. The first one, it's always going to be called constant. That's the y-intercept. The second one, it's the value associated with the predictor variable, ours, that is the slope. And so we can take those two values and we can, starting with our sort of general equation for the line of best fit, we can fill in values for B0 and B1, and that gives us our line of best fit. Now, the predicted population mean response for any given value of x can be calculated using the line of best fit. So, for example, let's suppose we're curious to know if a student uses a training program for 10 hours, what do we expect to see on average for their playing strength after those 10 hours? And so if we put a vertical line at 10 hours, you see where it intersects the line of best fit. That's the fitted value. That's the y hat. And we can calculate that y hat simply by taking 10 hours and putting it in where we see x in this linear equation. So y hat equals, we have an intercept, 769. We have a slope, 2.248. And you see x has been replaced by 10 hours. So multiplying 10 hours by the slope and then adding those numbers together gives us our predicted value. Now, it's important to realize that this y hat is a predicted population mean response. It's the predicted response that we should see on average for students who study for 10 hours, who use the chess training program for 10 hours. Okay. So, here is some data that I generated to sort of display the idea. So we have in total, let's see, we have 25 students. So there's 25 blue circles, each of those representing one individual student. So we're going to look at one of those data points specifically. For this particular student, they studied or used the chess training program for 45 hours. And at the end of the month, their chess playing strength was 859. The model predicts their chess playing strength to be something different. So that's marked in red. That predicted chess playing strength we could obtain by taking the linear equation, plugging in 45 hours where we see x, and then doing the calculation, and we get 870. So the observed value for that particular student was a playing strength of 859. The predicted value for that same student is a playing strength of 870. The difference between those is called the residual error. So the residual error is just a difference between what was observed and what was predicted, what would be predicted. In this case, that residual error is minus 11. It's negative because the observed value is below the line of best fit. If the observed value was above the line of best fit, we would get a positive residual. And so this diagram emphasizes really the key component or the key sort of notion behind the whole regression stuff. And that is, we have three sources of variation. So for every individual observation has a corresponding fitted value and a corresponding residual error. So that what that means is we have three sources of variation, which, by the way, we measure using sum of squares. What are those three sources? We have the observations in blue, we have the fitted values in red, And we have the residuals, which is just the difference between those things. So 3 sources of variation. And so we can actually see that when we conduct an analysis in Minitab. One of the things that Minitab will give you is a table called the analysis of variance table. This is an analysis of variance table for regression. And how do I know it's for regression? You can see under the word source is the word regression. So what do we see here? We see that source represents sources of variation. We have 3 sources of variation that correspond to the 3 components of our regression analysis. Those same 3 components we just mentioned. So we have the total variation in the observations, the y values. We have variation in the fitted values, and we have variation in the residuals. And so how do we measure variation? We measure variation using a sum of squares. And so you see in the table in the 3rd column, SS represents sum of squares. Each of these sources of variation has a corresponding measure, a sum of squares that's measuring the variation. Now, I'd like you to take out your calculator, punch in the sum of squares for regression, 8598.7. Just punch that into your calculator. And now go plus, and then add to it the sum of squares for the error, the 3257.0. So press equals, and what do you get? What do you notice? The sum of squares for the regression plus the sum of squares of error, they add up to the total sum of squares. So this is a really important concept in regression. Right, so just a little bit of symbols here. The sum of squares of regression, you can see the symbol for that is SS. We put a little y hat in the corner. So this would represent the variation of the fitted values. The sum of square of errors, we put a little e in the corner. That would be the sum of squares of the residual errors. And the last one will be the sum of squares with a little y down in the corner. That would be the total variation of the observations. And so the point here is that the total variation in the observations is partitioned between the fitted values and the residuals. And what I mean by partition, it means that total variation is split. Some of it is going to go into the fitted values, the y hats, and some of it is going to be left over for residuals. And so to put it in another way, the total variation in the observed y values, which you can see here highlighted in purple, is composed of a systematic component, that is the regression line. The fitted values represent a systematic component of variation, a linear component of variation. So the total variation is composed of a systematic component, that is the regression line or the fitted values, and a random component, which is just due to individual differences. So this is a key concept, and that brings us now to the concept of coefficient of determination. So you might recall from 2208, I'm sure you talked about coefficient of determination. What is it? It's the percentage of total variation that's apportioned to the fitted values. So what am I talking about? Here in the model summary, we can see we have this thing called R squared. That is the coefficient of determination. Now I want to show you how that coefficient of determination relates to our measures of variation for regression and for total. So what are we seeing here? We're taking on the bottom of this fraction the total variation in the observations. And on top of the fraction is the part of that total variation that is going toward the systematic component. In other words, it's the part of the variation in the observations that is linearly systematic. Or another way of saying it, it's the variation of the fitted values. If you calculate this ratio and multiply by 100 to get a percentage, you can see that is exactly R squared. And so R squared is the proportion of the total variation in your observations that goes toward the fitted values, or in other words, that goes toward the systematic component of the total variation. So there's a couple of ways you can actually describe this R-squared statistic, this coefficient of determination. One way is we could say, in this particular instance, we could say the systematic component of variation in this instance accounts for 72.53% of the total variation in the observed values. We could say it that way. But there's other ways that you can describe it. So let's just go through those. So R squared, the coefficient of determination, is the proportion of the total variation in the observed Y values that is captured by the fitted model, or you could say that is explained by the predictor variable. The important thing is this is a systematic component of that total variation. So the total variation, of course, as I'm explaining here, is partitioned. So SS with a little y in the corner, that's the variation of your observed values. That's split between a systematic component, that's SSY hat, and a random component due to individual differences, that's SS with a little e in the corner. Now, the greater the variation in the fitted values, so that's the SSY hat, the bigger that number is, the less variation there will be left over for the residual errors. And why do I say it that way? Because remember, the sum of squares of y hat, the variation of your fitted values, plus the variation of your residuals, they have to add up to a constant. And so if one of those numbers gets bigger, the other one has to get smaller to compensate. So the bigger the variation due to the systematic component in your data, the less variation there will be left over for the random component. And so what does that mean in the end? It means the greater the sum of squares of your fitted values, the greater the variation, the systematic variation in your data, the less scatter there will be in the data cloud. Now, I realize that's kind of abstract, so I've got some diagrams just to emphasize the difference. So here on the left, you see a scatter plot where there is a substantial amount of scatter about the line of best fit. And so in this case, if you were to calculate the regression coefficient for this data, well, let me ask you, would the regression coefficient be big or small? Well, hopefully you're thinking it should be small, right? Because there's a lot of scatter in the data. You might recall from 2208, the more scatter you have in your data, the smaller the regression coefficient. So in this case, the regression coefficient is exactly 0.50. You might also recall that the coefficient of determination is the regression coefficient squared. So if you square this number, you get 0.25. No, sorry, I had these in the wrong order. So let's go back. Let's look now at the right-hand side. What do you see on the right-hand side? Comparing with what you saw on the left, what do you see in terms of scatter? There is less scatter in the plot on the right-hand side. So the coefficient the regression coefficient is now closer to 1. If we square these regression coefficients, we get the corresponding coefficients of determination. So on the left, it's only 0.25. On the right, it's 0.72. So what does this mean? If we look on the left side, what this tells us is the total variation in these observations, in the y values. Of that total variation, 25% of it is systematic. It's going into the sum of squares of y hat. 75%, the remaining 75%, it's just due to random differences between individuals. That goes into the sum of squares of error. By contrast, on the right-hand side, R squared is 0.72. So that means that of the total variation in the y values, 72% of that is systematic. It's going into the sum of squares of y hat. And only, 28% is left over, which is due to individual differences. So you can see that the more scatter you have in your data, the smaller is the coefficient of determination. The less scatter you have, the bigger is that coefficient. And that's all comes down to the fact that the total variation in that data cloud is split between a systematic component, that's your sum of square of y hat, and a random component, that's your sum of square of errors. Okay, so just a couple more points to make before we finish up. The standard deviation of the residuals provides an alternative measure of scatter. And so in the model summary that you get from Minitab, the first number that has the symbol S, that's actually the standard deviation of the residuals. Now here I'm showing you the formula for standard deviation. you can see that basically we're looking at a sum of squares for the residuals. We're dividing by n minus 2. That n minus 2 we will discover later is a degrees of freedom. That will be explained later. And then we take a square root to make that a standard deviation. So this is a standard deviation for the residuals, and you can see that that standard deviation is exactly what you see in the table. Now, by the way, this is a good point to remind you that there was that video that I made. It's just under 20 minutes long. It explains the relationship between variation, variance, which we haven't talked about yet in this video. So variation, variance, and standard deviation. I strongly recommend you watch that video again. This is a good time to look at that again, just to refresh your memory about these concepts. And indeed, I know that maybe less than half of you have watched this video so far, because I can see the number of views there were. I strongly recommend you watch this video in the next few days. And the reason is the explanation for variation, variance, and standard deviation, how these things relate to each other. That explanation is going to make this unit on regression and the next unit on analysis of variance is going to make those much easier to understand. So I strongly recommend that you have a look at that video. Okay, so regression checklist. Here we're going to talk about the conditions under which regression is the appropriate model to use. So first, the predictor and response variable must be quantitative. Second, the scatter plot must suggest a linear association. So it must look like there's a linear trend in the data. Third, the residuals must be structureless. So this means that there's no trend in the residuals. There's no trumpeting or thickening of the plot. I'm going to show you some examples to make sure you understand what that condition is all about in just a minute. The residuals also must be approximately normal in distribution. So you might recall that the way we can tell whether a data set is consistent with a normal distribution, we make a normal probability plot. So I'm going to show you one of those in a minute. There also must be no outliers or what we call influential data points. I haven't reviewed the concept of influential data points. I'm not sure if I will or not, so you might want to just Google that or look at your notes from 2208 just to remind you of what an influential data point is. I'll leave that one to you. Also, there must be no evidence of a lurking variable. I'm also going to leave a lurking variable, that concept. I'll leave that for you to Google and to refresh your memory from 2208. So let's just talk a little bit about what residuals need to look like. So here in this plot, we're looking at these data points. This is for a completely different set of data. We have the fitted value for a linear regression model on the horizontal axis, and we have the residuals on the vertical axis. And so what we're seeing here is what we call thickening of the plot or trumpeting. In this case, you can see that the spread in the vertical direction increases as we move from left to right. So if your regression model is appropriate, you should see that the spread in the vertical direction is roughly the same as you move from left to right. Here it's not the same, it's small and it gets bigger as you move to the right. So this is related to what we would call in 2208 the thickening of the plot condition. And it states that if there is thickening of the plot in the residuals versus fits, as you see here, then the regression model is not appropriate. So now on the bottom here, you're looking at another example. This is again is a completely different data set. Here we have the fitted value on the horizontal axis, the residuals on the vertical axis. If you look at the spread in the vertical direction, it's about the same as you move from left to right. The actual thickness of the data is more or less the same, but there is a trend in these residuals. And so a trend is not a good thing. The linear enough condition states that if there is any trend in the residuals versus fits, then the regression model is not appropriate. So if you collect some data, you perform a regression, and at the end you get your plots of the residuals, Minitab will give you these plots. If you see anything like thickening of the plot or you see a trend, then you know that the regression model was not appropriate. Now, what do the residuals look like when the regression model is appropriate? Here's a nice example. This, again, a completely different data set. Fitted value on the horizontal axis, residuals on the vertical. What do we see here? The spread in the vertical direction is roughly the same as we move from left to right. And there is no trend evident in the residuals. So this is what we want to see. And this is a case where we can say, yes, the linear model was appropriate for this data. So that's just about it. I think the last thing we'll do, we're now going to go back to the data for the chess players, and we're going to look at the residual plots for that data. So just as an example, so here's that data where we have on the horizontal axis the number of hours a student spent using the training program for that 1 month. On the vertical axis is their chess playing strength at the end of the month. We can see the line of best fit. We can see R squared is 72.5%. So that's telling us that, what is it telling us? It's telling us that of the total variation in the observations and the Y values, the 72.5% of it is systematic, and 100% minus that number is random due to individual differences. So this is a pretty good fit overall. But we might have some problems because if you look in the upper right-hand corner, we got one data point that looks a bit unusual. So let's look at the residuals for this fit. So in the top left-hand corner, we see a normal probability plot. A normal probability plot is used for one thing, and that is to determine whether the data is consistent with a normal distribution. So in this case, well, what are we looking for? Let's pause for a second. What are we looking for? We're looking to see if those data markers are approximately in a straight line. And here you can see most of the data markers are in a straight line, but we do have one unusual data point, which is sort of far away from the rest. So that's indicating that that data point might be problematic. Looking at the top right-hand side, we have fitted values on a horizontal axis, residuals on a vertical axis. And what do we see in that plot? Do we see thickening of the plot? Probably not. Do we see a trend? I would say yes. There is a linear trend in that data. And furthermore, there's one unusual data point with a very large residual. Looking now at the bottom left-hand corner, that's the histogram of the residuals. We can see, well, it's almost kind of unimodal, roughly symmetrical, but for that one outlying data point. So that outlying data point looks like it's going to be a problem. And then in the bottom right-hand corner, we have the observation order versus the residuals. In this scenario, the order of observation doesn't really matter. It's not relevant. But again, we can see that we do have one data point that looks problematic. So if I was doing this analysis with real data, at this stage, I would want to remove that one unusual data point, set it aside, and then repeat the analysis and look at the residuals again to make sure they look okay. So this is just one example of the kinds of things that we need to do when we look at residuals. So finally, I want to just finish up by telling you what is to come. So after this coming week, I'll be back. And when I come back, we're going to continue with regression. And so looking at this Minitab output, you can see that we have the coefficients. We talked about how you use the coefficients to write out the line of best fit. But I want you to notice something. These are sample coefficients. And so what do I mean by that? Well, if we took another sample and we did the same analysis, our B0 and B1, our slope and intercept, would probably be different. And so what that means is B0 and B1, our sample slope and sample intercept, are random variables. So these are random variables. And so that means they have an associated measure of uncertainty, associated standard error. So SE coefficient, those two numbers give the standard error of the coefficients. And they also have t-statistics. Each coefficient has a corresponding t-statistic, and you can see there's a p-value. So the question would be, what is the hypothesis test that we're conducting using this test statistic? Well, generally, the hypothesis is under the null. The constant term, the intercept, is 0. The alternative being it's not 0. And then we can conduct a test saying, as a null, the slope is 0. And as an alternative, it is not 0. So what we're going to see in the end is that whereas B0 and B1 are sample coefficients, which will change with each sample, we also have population coefficients, and they're given the symbols beta 0 and beta 1. See that funny B? That's the Greek letter beta. So beta 0 and beta 1 are population coefficients. They're fixed values. They're unknown. And we want to make inferences about what those values might be. And how do we do that? Well, we do the fit. We get our sample coefficients. And then we do statistical tests to see whether those sample coefficients are 0 or not. So this is the kind of thing that is about to come. So you can see, again, in the end, it's all going to be about hypothesis testing. And in this case, because we're working with a t-distribution, we're also going to be looking at confidence intervals for these population values. Okay, so that's all. So yeah, I hope that was good for you. I enjoyed doing that. Yeah, I guess that's going to be it for this week. I plan to see you in the following week, and I'll let you know how it goes for us during this week. That's all. Bye for now, and I'll see you again sometime. Bye.